Imagine watching 96% of all life on Earth disappear within about 60,000 years. This nightmare scenario has already happened, not once, but 5 times in our planet's history. The Great Dying 252 million years ago obliterated nearly every living thing, leaving Earth a barren wasteland. But scientists estimate modern extinction rates are now 1,000 to 10,000 times higher than natural background levels, suggesting we may already be in a sixth extinction phase. Vertebrate populations have declined by 68% since 1970 alone. The question is no longer if we'll witness another great dying, but how much of life will survive our own. To understand what we're facing, we must first examine the catastrophic episodes that nearly erased life before. The Big Five, when Earth nearly died. Earth's history reveals 5 catastrophic episodes when life nearly vanished completely. These mass extinctions represent the closest our planet has come to total biological collapse. Each event eliminated more than 75% of all species, reshaping the evolutionary trajectory of life itself. The fossil record preserves these ancient disasters like pages in a book of planetary catastrophes, each chapter telling the story of how Earth's biosphere can be pushed beyond its breaking point. The pattern repeats with terrifying consistency across geological time. Every few hundred million years, some combination of climate change, volcanic activity, or cosmic impact overwhelms the planet's capacity to sustain complex life. These aren't random accidents, but systematic breakdowns in Earth's life support systems. The regularity suggests that mass extinctions operate as planetary reset buttons, wiping the slate clean for new evolutionary experiments to begin. The Ordovician extinction struck 445 million years ago when Earth transformed into a frozen wasteland. Massive ice sheets expanded from the poles, locking up so much ocean water that sea levels dropped by 100 meters. Tropical seas that had teemed with marine life suddenly drained away, leaving vast underwater ecosystems high and dry. The continental shelves that supported 85% of all species became barren, exposed rock. This glacial apocalypse lasted only 1 million years, but the speed of change proved catastrophic. Species that had evolved in warm, shallow seas couldn't adapt fast enough to survive in the new frozen world. The Ice Age ended as abruptly as it began, triggering a second wave of extinctions. Glaciers melted rapidly, causing sea levels to rise again and flooding the continental margins. Species that had somehow survived the freezing phase now faced drowning as their refugia disappeared underwater. The double blow of glaciation, followed by rapid warming, created a 1-2 punch that eliminated most of the Ordovician's marine ecosystems. Only the most adaptable organisms survived this planetary temperature swing. The late Devonian crisis, 375 million years ago, demonstrates how evolutionary success can become evolutionary suicide. The first forests had finally colonized the land, transforming barren continents into green landscapes. These massive tree-like plants, primitive relatives of modern club mosses, grew 30 meters tall and spread across empty land masses. Their roots penetrated deep into bedrock, breaking down rock formations and creating soil for the first time in Earth's history. This forest revolution triggered an environmental disaster. The massive root systems caused unprecedented erosion, washing billions of tons of sediment and nutrients into the oceans. Rivers carried phosphorus and nitrogen from the weathered rocks directly into marine ecosystems. The nutrient influx created massive algal blooms that consumed all available oxygen in the water. Ocean dead zones expanded across continental shelves, suffocating marine life on a global scale. The newly evolved trees also altered the carbon cycle in ways that destabilized the climate. Their photosynthesis pulled enormous amounts of CO2 from the atmosphere, triggering global cooling. At the same time, their decay released organic compounds that further depleted ocean oxygen levels. The forests that represented life's first major conquest of land inadvertently poisoned the marine ecosystems that had supported biodiversity for hundreds of millions of years. Scientists measure extinction magnitude by comparing current species loss rates to background extinction rates preserved in the fossil record. During normal periods, species disappear at a rate of roughly 1 to 5 species per million species per year. This background rate represents the natural turnover of life, as some species evolve, while others go extinct through ordinary evolutionary processes. Mass extinctions occur when species disappear at rates 10 to 100 times higher than this background level. The Big Five events all exceeded this threshold, with some reaching extinction rates 1,000 times above normal levels. These catastrophic spikes in species loss appear as sharp boundaries in the fossil record, marking distinct geological periods where life on Earth fundamentally changed. The geological timescale reveals the true scope of these planetary disasters. Each mass extinction represents the culmination of environmental changes that built up over millions of years. The Ordovician glaciation didn't happen overnight, but developed as atmospheric CO2 levels gradually declined. The Devonian forest revolution unfolded over tens of millions of years before reaching its toxic tipping point. These timescales dwarf human experience, but provide crucial context for understanding how planetary systems can shift from stability to collapse. Each extinction event left permanent scars in Earth's evolutionary history. The Ordovician extinction eliminated entire groups of marine animals that never re-evolved. The Devonian crisis ended the dominance of armored fish and paved the way for the rise of sharks and bony fish. These evolutionary bottlenecks channeled life down different paths, creating the modern biosphere through a process of elimination and renewal. The Big Five extinctions also reveal which types of species survive planetary catastrophes. Generalist species with broad environmental tolerances consistently outlast specialists adapted to specific conditions. Small-bodied organisms fare better than large ones during resource shortages. Species with rapid reproduction rates can recover faster than those with long generation times. These survival patterns emerge repeatedly across different extinction events, suggesting universal rules for biological resilience. Current extinction rates already exceed the thresholds that define mass extinctions in the geological record. Species are disappearing at rates comparable to the Big Five, but compressed into decades rather than millennia. This temporal compression represents something unprecedented in Earth's history. Previous mass extinctions unfolded over geological timescales that allowed some species to migrate, adapt, or evolve new survival strategies. The current crisis is happening too fast for these evolutionary responses to operate effectively. Yet even among these 5 catastrophic episodes, one stands apart as the ultimate test of life's resilience. This event pushed Earth closer to complete biological annihilation than any other crisis in the planet's history. The Great Dying, Earth's closest call. The Permian-Triassic extinction event 252 million years ago represents the closest Earth has ever come to complete biological annihilation. Scientists call it the Great Dying because 96% of all marine species vanish from the fossil record within a geological instant. This catastrophe dwarfs all other mass extinctions in Earth's history. While previous events eliminated 75% to 85% of species, the Great Dying pushed life to the absolute brink of total collapse. Only 4% of marine species survived this planetary apocalypse, making it the most severe biological crisis in the known history of life. The Great Dying resulted from a perfect storm of catastrophic events that converged to create an unlivable planet. Multiple environmental disasters struck simultaneously, each amplifying the destructive power of the others. Massive volcanic eruptions, climate change, ocean acidification, and atmospheric poisoning combined into a cascade of destruction that overwhelmed Earth's capacity to sustain complex life. The speed and severity of these changes prevented evolutionary adaptation or migration to safer environments. The Siberian Traps volcanic eruptions triggered this global catastrophe through sheer volcanic violence on an almost incomprehensible scale. These eruptions began around 252 million years ago and continued for approximately 2 million years. The volume of lava released could have covered the entire continental United States under a layer of molten rock 1 kilometer thick. The Siberian Traps covered an area of 7 million square kilometers, roughly the size of Australia, with volcanic flows and ash deposits. The volcanic activity released enormous quantities of greenhouse gases into the atmosphere. Carbon dioxide levels increased by 2,000 parts per million above pre-eruption levels. Sulfur dioxide emissions created acid rain that fell across the planet for thousands of years. Methane released from burning coal deposits and organic matter added another powerful greenhouse gas to the atmospheric mix. The volcanic emissions also included toxic metals like mercury and arsenic that poisoned terrestrial and marine ecosystems. These massive gas emissions triggered a runaway greenhouse effect that raised global temperatures by 10 degrees Celsius above pre-extinction levels. The planet's average temperature reached 40 degrees Celsius, making much of Earth's surface uninhabitable for complex life. The polar regions, which had been temperate before the eruptions, became tropical zones. The equatorial regions experienced temperatures approaching 60 degrees Celsius, creating vast dead zones where nothing could survive. The extreme warming fundamentally altered ocean circulation patterns. The temperature difference between poles and equator drives ocean currents that distribute heat and nutrients around the planet. As this temperature gradient flattened, ocean circulation slowed dramatically. Stagnant water bodies developed across the seafloor, creating perfect conditions for the growth of anaerobic bacteria that produce hydrogen sulfide gas. Hydrogen sulfide production reached catastrophic levels as bacterial populations exploded in the oxygen-depleted oceans. This toxic gas bubbled up from the depths and accumulated in the atmosphere, creating a poisonous cocktail that turned the sky green and made the air unbreathable for most life forms. Hydrogen sulfide concentrations reached levels that would kill most oxygen-breathing organisms within minutes of exposure. The gas also destroyed the ozone layer, allowing deadly ultraviolet radiation to reach Earth's surface. Ocean acidification accompanied the atmospheric changes as massive amounts of carbon dioxide dissolved into seawater. The pH of the oceans dropped by 0.7 units, making the water so acidic that calcium carbonate shells began dissolving. Marine creatures with shells and skeletons found their protective structures literally dissolving around them while they were still alive. Coral reefs, shellfish, and other calcifying organisms experienced widespread shell dissolution as the ocean chemistry became increasingly corrosive. The combination of warming, acidification, and toxicity created a marine environment that could support only the most primitive forms of life. Complex marine ecosystems collapsed as food chains disintegrated from the bottom up. Photosynthetic organisms died from the combination of toxic water and reduced sunlight penetration. Filter-feeding organisms suffocated in the hydrogen sulfide-rich water. Predators starved as their prey disappeared. Terrestrial ecosystems suffered equally devastating losses. Forests disappeared across entire continents as trees died from the extreme heat, acid rain, and toxic atmospheric conditions. The fossil record shows a complete absence of coal formation for 5 million years after the extinction event, indicating that forests did not recover until well into the Triassic period. Soil formation ceased as plant roots no longer broke down rock and organic matter stopped accumulating. Atmospheric oxygen levels crashed to 10% during the Great Dying, less than half the current atmospheric concentration of 21%. This oxygen depletion created conditions equivalent to living at the altitude of Mount Everest at sea level. Most complex organisms require oxygen concentrations above 15% to maintain normal metabolic functions. The reduced oxygen availability made it impossible for large animals to obtain enough energy to survive. Only the most adaptable generalist species survived this planetary purge. Organisms that could tolerate extreme environmental conditions, switch between different food sources, and reproduce rapidly had the best chances of survival. Specialist species adapted to specific environmental conditions were eliminated when those conditions disappeared. Large organisms with high metabolic requirements died out first, while small organisms with low energy needs persisted longer. The recovery from the Great Dying took approximately 10 million years, longer than any other mass extinction event. The severity of environmental damage meant that ecosystems had to rebuild from almost nothing. New evolutionary lineages emerged to fill the ecological niches left vacant by extinct species. The survivors eventually gave rise to the dinosaurs and other groups that would dominate the Mesozoic era. Modern carbon dioxide emission rates exceed even the catastrophic pace of the Great Dying. Current annual emissions from human activities release carbon dioxide faster than the Siberian Traps eruptions did 252 million years ago. Ocean acidification is already occurring at rates that exceed the Permian-Triassic event. Global temperatures are rising faster than during the Great Dying. The Great Dying serves as a warning of what can happen when multiple environmental stressors combine to push Earth's life support systems beyond their limits. Yet among all the species that faced this ultimate test of survival, one group had already proven their resilience through hundreds of millions of years of evolutionary success. Trilobites, the ultimate survivors who couldn't survive. Trilobites dominated the oceans for 270 million years, surviving longer than any other complex animal group. These marine arthropods ruled the seas from 521 million years ago during the Cambrian explosion until the Great Dying eliminated them forever. No other animal lineage has matched their combination of longevity, diversity, and ecological dominance. When trilobites first appeared, life on Earth was confined to the seas, and when they disappeared, the continents were covered with forests and populated by reptiles and early mammals. The evolutionary innovations that trilobites developed remain unmatched in the animal kingdom. They created the first compound eyes in Earth's history, using hundreds of individual lenses made of pure calcite crystal. Each lens focused light with mathematical precision, creating a mosaic image that could detect movement and changes in light intensity. The calcite lenses were perfectly transparent and resistant to scratching, providing clearer vision than the organic eyes of most modern animals. Some trilobite species developed eyes with over 15,000 individual lenses, giving them nearly 360-degree vision that could spot predators and prey from any direction. Their visual systems varied dramatically across different species and environments. Deep-water trilobites evolved enlarged eyes to capture the faintest traces of light filtering down from the surface. Shallow water species developed complex eye structures that could detect polarized light and see ultraviolet wavelengths invisible to most other animals. Some burrowing trilobites lost their eyes entirely, while others developed eye stalks that could extend above the sediment while the rest of the body remained hidden. Multiple extinction events tested trilobite resilience throughout their long history, and they consistently found ways to survive planetary catastrophes that eliminated other animal groups. The Ordovician extinction that wiped out 85% of marine species left trilobites decimated but not destroyed. Surviving populations evolved new body forms and feeding strategies to exploit the changed post-extinction environment. They developed stronger shells, more efficient gill systems, and improved mobility to cope with fluctuating sea levels and oxygen availability. The late Devonian extinction challenged trilobites again as ocean acidification and oxygen depletion eliminated many of their traditional food sources. They responded by evolving more diverse feeding mechanisms, including filter feeding appendages and specialized chemical sensors that could detect organic matter in the water column. Some species developed the ability to burrow deeper into sediments where oxygen levels remain stable. Others evolved streamlined body shapes for more efficient swimming in oxygen-poor waters. Trilobite defense mechanisms evolved into sophisticated systems that protected them from the numerous predators that shared their marine environment. Many species developed elaborate spines that made them difficult to swallow or attack. The spines were not just simple projections, but complex structures with barbs and hooks that could inflict serious damage on any predator attempting to consume them. Some trilobites grew spines longer than their entire body length, creating a formidable defensive barrier around their vulnerable soft parts. The ability to roll into a tight ball provided another crucial defense mechanism. Trilobites could tuck their heads under their bodies and curl their flexible tails forward, creating a completely enclosed sphere protected by hardshell segments. This enrollment behavior was so effective that many trilobite fossils are found in the enrolled position, preserved exactly as they died while defending themselves. Chemical detection systems gave trilobites a crucial advantage in finding food and avoiding danger. They developed specialized appendages covered with chemoreceptors that could detect dissolved organic compounds in the water. These chemical sensors were more sensitive than those of most modern marine animals, allowing trilobites to locate food sources buried in sediment or detect the approach of predators from considerable distances. Trilobite lifestyles diversified into every available ecological role in ancient marine ecosystems. Bottom-dwelling species developed flattened bodies and wide heads for efficient sediment processing. They would plow through seafloor mud, extracting organic matter and small prey with specialized feeding appendages. Free-swimming predatory trilobites evolved streamlined bodies and powerful appendages for catching mobile prey. These species developed enlarged eyes and rapid swimming abilities that allowed them to pursue fish, cephalopods, and other fast-moving animals. Filter-feeding trilobites occupied the ecological niche now filled by many modern marine animals. They developed specialized appendages with fine bristles that could strain plankton and organic particles from the water column. These species often lived in large aggregations, creating the first underwater animal communities that could process enormous volumes of seawater. Ice ages, asteroid impacts, and climate shifts repeatedly challenged trilobite survival throughout their geological history. They weathered the severe glaciation events that froze much of the planet's surface and dramatically lowered sea levels. When asteroid impacts filled the atmosphere with dust and debris, trilobites survived in the depths while surface-dwelling animals perished. Climate oscillations that alternated between greenhouse and icehouse conditions tested their adaptability repeatedly, and they consistently found ways to adjust their physiology and behavior to match changing conditions. Their dependence on oxygen-rich seafloors ultimately became their fatal weakness when the Great Dying transformed Earth's oceans into toxic, oxygen-depleted environments. Trilobites had evolved complex gill systems that required steady supplies of dissolved oxygen to function properly. Their active lifestyles and sophisticated sensory systems demanded high metabolic rates that could only be sustained in well-oxygenated water. When hydrogen sulfide, poisoning, and oxygen depletion spread across the seafloor, trilobites had no evolutionary escape route. The Great Dying eliminated trilobites after 270 million years of evolutionary success. Their extinction demonstrates that no amount of previous survival success can guarantee future persistence when environmental conditions exceed biological limits. Trilobites had survived 4 previous mass extinctions, evolved thousands of different species, and colonized every marine environment on Earth. Yet they could not adapt quickly enough to survive the rapid environmental changes that characterized the Great Dying. The trilobite story reveals that evolutionary success offers no guarantee against mass extinction when environmental change exceeds the limits of biological adaptation. Even the most successful species can face sudden, catastrophic events that render millions of years of evolutionary refinement irrelevant in an instant. The asteroid that rewrote life's rules. 66 million years ago, a mountain-sized asteroid traveling at 20 kilometers per second slammed into Earth with the force of 10 billion atomic bombs. The impact occurred in what is now the Yucatan Peninsula in Mexico, but the devastation spread across the entire planet within hours. This single cosmic collision ended the age of dinosaurs and rewrote the rules of life on Earth. The asteroid measured approximately 10 kilometers in diameter, roughly the size of Manhattan, and its hypervelocity impact released more energy than all the world's nuclear weapons combined. The immediate devastation created a crater 180 kilometers wide and 20 kilometers deep, vaporizing bedrock and hurling billions of tons of material into the atmosphere. The impact penetrated through sedimentary layers and struck sulfur-rich bedrock, releasing massive quantities of sulfur dioxide gas. The collision generated temperatures exceeding 10,000 degrees Celsius at the impact site, instantly vaporizing everything within hundreds of kilometers. Shock waves from the impact triggered earthquakes, measuring magnitude 10 or higher across the entire planet. The force of the collision launched debris into ballistic trajectories that carried molten rock fragments around the globe. These glowing projectiles rained down on every continent within hours of the initial impact, igniting wildfires wherever they landed. The debris cloud contained enough energy to raise atmospheric temperatures by several hundred degrees Celsius as the molten fragments re-entered Earth's atmosphere. Forests across North America burst into flames first, followed by vegetation on other continents as the debris shower continued. A global firestorm ignited forests across continents within hours of impact as the ballistic debris continued falling from the sky. The fires were unlike anything in Earth's history, spreading faster than any natural wildfire because the ignition sources fell simultaneously across vast areas. Smoke and ash from burning forests combined with impact debris to create a choking atmosphere that blocked sunlight across the planet. The firestorm consumed an estimated 25% of all terrestrial vegetation, eliminating food sources for herbivorous animals and disrupting photosynthesis on a global scale. The impact winter that followed blocked sunlight for months, collapsing food chains worldwide and creating conditions more severe than any ice age. The combination of soot from global wildfires and pulverized rock from the impact created a dense atmospheric shroud that reduced sunlight penetration by 99%. Surface temperatures dropped by 20 degrees Celsius in some regions as the planet entered a period of near-total darkness. Photosynthesis ceased almost completely, causing plants to die and eliminating the foundation of all terrestrial food webs. This single catastrophic event eliminated 75% of all species on Earth, including all non-avian dinosaurs that had dominated terrestrial ecosystems for 165 million years. The extinction selectivity followed clear patterns based on body size, metabolism, and ecological niche. Large animals with high metabolic requirements died, first as food sources disappeared and temperatures dropped. Herbivorous dinosaurs starved when plant productivity ceased, followed by carnivorous species as their prey vanished. The sulfur dioxide released from the impact site created acid rain that persisted for years after the initial event. The impact had struck sedimentary rocks rich in sulfur compounds, vaporizing these materials and injecting them into the stratosphere. The sulfur dioxide combined with water vapor to form sulfuric acid, which fell as acid rain across the planet. This acid precipitation poisoned freshwater systems, damaged plant tissues, and created hostile conditions for any organisms that had survived the initial impact and firestorm. Some dinosaurs actually survived this catastrophe by evolving into birds, demonstrating that even the most severe extinction events can create opportunities for evolutionary innovation. The dinosaur lineages that survived possessed specific characteristics that proved advantageous during the crisis. They were small-bodied, had efficient metabolisms, and could exploit diverse food sources including seeds, insects, and carrion. Their feathers provided insulation during the impact winter, while their ability to fly allowed them to search for food across wide areas. The survival of birds reveals how chance and pre-existing adaptations determine extinction outcomes. The dinosaur groups that became birds had evolved flight capabilities millions of years before the asteroid impact. This flight ability proved crucial for survival because it allowed them to escape local environmental disasters and search for food resources across large distances. Their small body size meant they required less food than large dinosaurs, while their warm-blooded metabolism helped them survive the cold conditions of the impact winter. Modern asteroid surveys have identified thousands of near-Earth objects that could potentially trigger similar catastrophes today. Smaller asteroids than the one that killed the dinosaurs could still cause regional devastation and global climate disruption. An asteroid just 1 kilometer in diameter could eliminate entire countries and trigger worldwide crop failures. The frequency of such impacts means that statistically, Earth experiences civilization-threatening asteroid impacts every few 100,000 years. The asteroid impact that ended the Cretaceous period proves that sudden, unpredictable events can instantly reshape the entire tree of life. Unlike gradual environmental changes that allow species time to adapt or migrate, asteroid impacts create immediate global catastrophes that overwhelm biological defenses. The randomness of such events means that evolutionary success offers no protection against cosmic accidents. The dinosaurs had survived for 165 million years through multiple climate changes and extinction events, yet they could not survive a single day when a mountain-sized rock fell from space. This cosmic lottery continues today, with Earth's biosphere remaining vulnerable to random destruction from space. The asteroid that killed the dinosaurs was neither the largest nor the smallest object capable of causing mass extinction. Impacts of similar magnitude occur roughly every 100 million years, making them rare on human timescales but inevitable over geological time. Yet while asteroids represent dramatic and visible threats, another extinction mechanism operates with far more subtlety, appearing in every major extinction event throughout Earth's history without the spectacular fireworks of cosmic impacts. The hidden killer, ocean acidification through time. This chemical transformation dissolves the foundation of marine life through a process so gradual that entire ecosystems can collapse before the danger becomes apparent. Ocean acidification occurs when carbon dioxide dissolves into seawater, creating carbonic acid that fundamentally alters ocean chemistry. The process happens invisibly and steadily, making it difficult to detect until the damage becomes irreversible. The fossil record reveals that ocean acidification has accompanied every mass extinction event over the past 500 million years, making it one of the most reliable predictors of biological catastrophe. Carbon dioxide absorption turns seawater into a corrosive bath that attacks the shells and skeletons of marine organisms. When atmospheric CO2 levels rise, the oceans absorb approximately 30% of the excess gas through surface water interaction. This absorption creates a chemical reaction that produces hydrogen ions, which lower the pH of seawater and make it more acidic. The process also reduces the availability of carbonate ions that marine organisms need to build their shells and skeletons. As acidity increases, the ocean becomes corrosive enough to dissolve calcium carbonate structures faster than organisms can produce them. The Paleocene thermal maximum 55 million years ago demonstrates what happens when rapid carbon emissions acidify the oceans. This ancient warming event occurred when massive carbon releases from volcanic activity and methane hydrate decomposition raised global temperatures by 5 to 8 degrees Celsius. The carbon emissions acidified the oceans so severely that many deep-sea organisms with calcium carbonate shells went extinct. The event lasted approximately 200,000 years, but the ocean acidification effects persisted for over 100,000 years after carbon emissions returned to normal levels. Deep-sea sediment cores from this period show a complete absence of carbonate shells in certain layers, indicating that the ocean became so acidic it dissolved existing shells on the seafloor. This dissolution event extended from the surface waters down to depths of 2,000 meters, affecting organisms throughout the water column. The recovery required tens of thousands of years as ocean chemistry gradually returned to normal and marine organisms could rebuild their populations. Rapidly changing ocean chemistry dissolves shells and skeletons of marine life through a process called undersaturation. When seawater becomes undersaturated with respect to calcium carbonate, the shells and skeletons of marine organisms begin dissolving spontaneously. This dissolution occurs even in living organisms, forcing them to expend enormous amounts of energy to maintain their protective structures. The process affects everything from microscopic plankton to large mollusks, creating stress throughout marine food webs. Carbonate ion depletion starves shell-building organisms of the chemical building blocks they need for survival. Marine organisms extract carbonate ions from seawater to construct their shells and skeletons through biomineralization. As ocean pH drops, carbonate ion concentrations decrease exponentially, making it increasingly difficult for organisms to access the materials they need. This depletion forces organisms to work harder to build the same structures, diverting energy from growth, reproduction, and other vital functions. Modern ocean pH has already dropped by 0.1 units since the Industrial Revolution, representing a 30% increase in acidity. This change has occurred over just 150 years, making it one of the fastest acidification events in the geological record. Pre-industrial ocean pH averaged 8.2, but current measurements show values of 8.1 across much of the world's oceans. The logarithmic pH scale means that this seemingly small change represents a dramatic shift in ocean chemistry. Current acidification rates exceed even ancient catastrophes in their speed and magnitude. The Paleocene thermal maximum acidified the oceans over thousands of years, while modern acidification is happening in decades. This acceleration gives marine organisms no time to adapt through evolutionary processes or migrate to less affected areas. Laboratory experiments show that many marine organisms experience reduced growth rates, reproductive failure, and increased mortality when exposed to projected future acidity levels. Coral reefs and shellfish are already showing signs of dissolution stress as ocean chemistry approaches critical thresholds. Coral bleaching events increasingly coincide with periods of high acidity, indicating that pH stress compounds the effects of warming temperatures. Shellfish farmers report declining harvest yields as oysters, clams, and mussels struggle to build shells in increasingly acidic water. Laboratory studies demonstrate that coral growth rates decrease by 15 to 20% when exposed to acidity levels projected for 2050. Ocean chemistry changes can trigger cascading ecosystem collapse as foundation species disappear and food webs unravel. Pteropods, tiny sea snails that form the base of many marine food chains, experience shell dissolution in acidic water. These organisms feed everything from salmon to whales, making their decline a threat to entire ecosystems. When pteropod populations crash, fish populations decline, affecting seabirds, marine mammals, and human fisheries. The current crisis facing marine ecosystems worldwide mirrors the acidification events that accompanied previous mass extinctions. The Great Dying featured severe ocean acidification that eliminated 96% of marine species. The Triassic-Jurassic extinction event included acidification that caused widespread coral reef collapse. These ancient events show that ocean acidification operates as both a cause and consequence of mass extinction, creating feedback loops that amplify ecological destruction. Modern monitoring systems detect acidification hotspots where marine ecosystems face immediate threats. The Arctic Ocean is acidifying twice as fast as tropical waters due to cold water's increased CO2 absorption capacity. Coastal upwelling zones experience periodic acidification events as deep CO2-rich water rises to the surface. The geographic variation in acidification rates means that some marine ecosystems will collapse before others, creating a patchwork of healthy and degraded ocean regions. This invisible chemical warfare against marine life represents just one component of humanity's unprecedented impact on planetary systems. The scale and speed of these changes are creating permanent markers that will remain embedded in Earth's geological record long after our civilization has passed. The Anthropocene, a new geological age of destruction. These geological signatures mark the beginning of the Anthropocene, a new epoch defined by humanity's permanent impact on Earth systems. Geologists recognize this as the first time a single species has left such comprehensive traces in the planet's geological record. The physical markers of human activity now appear in sediment cores, ice layers, and rock formations across every continent. These traces include artificial materials, chemical compounds, and isotopic signatures that have never existed in Earth's 4.6 billion year history. Future geologists studying our planet millions of years from now will identify a distinct boundary, layer marking, when humans fundamentally altered the geological processes that shape our world. Nuclear testing between 1945 and 1963 created radioactive signatures that will persist for millions of years in Earth's geological record. Over 2,000 nuclear weapons tests released artificial isotopes that dispersed globally through atmospheric circulation. Cesium-137, strontium-90, and other radioactive elements from these tests appear in ice cores from both poles, deep ocean sediments, and tree rings from every continent. The radioactive signature marks 1945 as a precise geological boundary that can be identified anywhere on Earth. These isotopes decay predictably over known time periods, providing future geologists with exact dating capabilities for Anthropocene deposits. The peak concentration of radioactive fallout occurs in sediment layers from the early 1960s, when atmospheric testing reached maximum intensity. This radioactive signature provides such a clear geological marker that scientists propose using it as the official beginning of the Anthropocene epoch. The radiation levels from this period exceed natural background radiation by factors of 10 to 100, creating an unmistakable boundary in the geological record that will remain detectable for geological ages. Concrete production has created more artificial stone than all natural rock erosion combined. Steel and aluminum production has scattered metallic particles across every continent. Glass manufacturing has introduced synthetic silicates into sedimentary deposits. These artificial materials accumulate in lake beds, river deltas, and ocean floors, creating permanent records of industrial civilization that will persist long after human structures crumble. The volume and distribution of these materials create geological deposits on a scale comparable to natural sedimentation processes. Plastic pollution has formed entirely new rock types found in ocean sediments and coastal environments. Microplastics now appear in sediment cores from the deepest ocean trenches to remote mountain lakes. These synthetic polymers create a permanent geological signature because they resist natural decomposition processes. Ocean currents concentrate plastic debris into massive accumulations that form new types of sedimentary deposits. Coastal areas show layers of plastic fragments mixed with natural sediments, creating artificial rock formations that geologists call plastiglomerates. Annual plastic production exceeds 300 million tons, with most ending up in landfills or marine environments. This plastic accumulation rate surpasses the natural formation of many sedimentary rocks. The chemical composition of these plastics includes synthetic compounds that have never existed in Earth's history, making them instantly recognizable to future geologists as markers of human industrial activity. These plastic rock composites will persist in the geological record for millions of years. Human activity has accelerated erosion rates beyond natural processes through agriculture, construction, and land use changes. Soil erosion from farming operations moves 10 to 40 times more sediment than natural weathering processes. Construction activities create erosion rates 100 times higher than natural levels. Dam construction traps sediments that would naturally flow to the oceans, altering river delta formation and coastal geology. Mining operations strip away rock layers that took millions of years to form, creating artificial geological exposures that will be visible for geological ages. Industrial chemicals and heavy metals now appear in ice cores and sediment layers across the planet. Lead concentrations in Greenland ice cores show a 50-fold increase since Roman times, with peak levels occurring during the 20th century. Mercury emissions from coal burning have distributed this toxic metal globally, creating concentration spikes in sediment cores from remote lakes. Synthetic chemicals like DDT, PCBs, and other industrial compounds appear in environmental archives from every continent. The concentration of heavy metals in modern sediments exceeds natural background levels by factors of 10 to 1,000. Copper, zinc, chromium, and other metals from industrial processes create geochemical anomalies in sedimentary deposits. These metal concentrations are so high that they will be detectable in rock formations millions of years from now. The distribution patterns reflect global industrial activity, with highest concentrations near urban and industrial centers. Future geologists will see our era as a distinct boundary in Earth's history comparable to the boundaries marking mass extinction events. The Anthropocene boundary will be defined by simultaneous appearance of artificial materials, radioactive isotopes, chemical pollutants, and altered sedimentation patterns. This combination of markers creates a more complex geological signature than any natural event in Earth's history. The boundary will be identifiable in rock formations, ice cores, coral reefs, and sedimentary deposits worldwide. The rate of environmental change now exceeds anything seen in the geological record, including the most rapid extinction events. Human-induced changes occur over decades rather than millennia, compressing environmental transitions that normally take geological ages. Atmospheric CO2 levels are rising 100 times faster than during the Paleocene thermal maximum. Ocean acidification is proceeding 10 times faster than during the Great Dying. These acceleration rates create environmental conditions that have never existed in Earth's history. This temporal compression prevents species adaptation through normal evolutionary processes. Evolution requires thousands of generations to produce significant genetic changes, but human-induced environmental shifts occur within single generations of most species. Species must either migrate to suitable habitats or face extinction. The speed of change also prevents ecosystem-level adaptations that might buffer species against environmental stress. Food web relationships that took millions of years to develop can collapse within decades when environmental conditions shift rapidly. The Anthropocene represents a fundamental shift in how geological processes operate on our planet. Human activity now moves more rock and soil than all natural erosion processes combined. We alter atmospheric and ocean chemistry faster than any geological process except major volcanic eruptions. The geological record will show that human influence on Earth systems equals or exceeds the impact of major geological forces that have shaped our planet for billions of years. But the true measure of this new epoch lies not just in the rocks and sediments we leave behind, but in the biological devastation we are creating in real time. The numbers don't lie. Modern extinction rates. Current extinction rates exceed natural background levels by 1,000 to 10,000 times, creating species loss at a pace that rivals the most catastrophic events in Earth's history. Natural background extinction rates, calculated from fossil records spanning hundreds of millions of years, show that typically 1 to 5 species disappear per million species per year during normal periods. This represents the natural turnover of life as some species evolve while others face evolutionary dead ends. Modern extinction rates now reach 100 to 1,000 species per million species per year, a rate of loss that exceeds the threshold scientists use to define mass extinction events. The comparison between modern species loss and the Big Five extinction events reveals striking parallels in both magnitude and scope. The Great Dying eliminated 96% of marine species over approximately 60,000 years, while current extinction rates suggest we could lose similar percentages of species within centuries rather than millennia. The Ordovician extinction that eliminated 85% of species occurred over 1 million years, but modern tropical deforestation eliminates entire ecosystems within decades. The asteroid impact that killed the dinosaurs created global devastation within months. Yet current habitat destruction operates continuously across multiple continents simultaneously. Scientists calculate extinction rates using sophisticated methods that combine fossil record analysis with modern species monitoring data. The fossil record provides baseline measurements by documenting how many species appeared and disappeared during different geological periods. Paleontologists count species appearances and disappearances in rock layers, then calculate average extinction rates over millions of years. Modern monitoring combines field surveys, camera traps, acoustic monitoring, and satellite imagery to track current species populations. Genetic analysis of museum specimens and field samples reveals how many distinct species actually exist within groups previously thought to represent single species. The calculations reveal that most extinctions now happen before species are even discovered by science. Taxonomists estimate that 8 to 15 million species exist on Earth, but only 1.5 million have been formally described and named. New species discoveries occur at rates of 15,000 to 20,000 per year, but extinction rates in tropical regions suggest that species disappear faster than they can be cataloged. Entire insect communities vanish when forests are cleared, eliminating species that existed for millions of years without ever being documented. Habitat fragmentation creates isolated populations doomed to genetic collapse through processes that guarantee extinction even when immediate threats disappear. Forest fragmentation divides continuous ecosystems into small patches separated by hostile environments. Animal populations trapped in these fragments face inbreeding depression as their gene pools shrink below viable levels. Small populations experience random genetic drift that eliminates beneficial traits and concentrates harmful mutations. The minimum viable population size for most vertebrate species ranges from 500 to 5,000 individuals, but fragmentation often reduces populations to dozens or hundreds of individuals. The mathematics of population genetics show that fragmented populations follow predictable paths toward extinction. Populations below 50 individuals face immediate genetic problems as inbreeding increases homozygosity and reduces fitness. Populations below 500 individuals lose genetic diversity faster than mutation can replace it, creating an extinction vortex where declining fitness reduces population size further. Island biogeography theory predicts that habitat fragments can only support populations proportional to their area, with smaller fragments supporting fewer species. Keystone species disappear and ecosystems unravel through cascading effects that eliminate entire food webs. Wolves control deer populations that otherwise overgraze vegetation and prevent forest regeneration. Sea otters control sea urchin populations that otherwise consume kelp forests and eliminate habitat for hundreds of other species. Large predators control herbivore populations that otherwise alter plant communities and change ecosystem structure. When keystone species disappear, their ecological roles cannot be filled by other species, leading to ecosystem collapse that eliminates multiple species simultaneously. Large mammals are disappearing at rates not seen since the last ice age, with populations crashing across all continents except Antarctica. African elephant populations have declined by 75% since 1980 due to poaching and habitat loss. Rhino populations have dropped by 95% since 1960, with several subspecies already extinct. Tiger populations have declined by 95% since 1900, surviving only in small, protected areas. The pattern extends beyond charismatic megafauna to include large mammals in every ecosystem type. Primate populations have declined by 60% since 1970, with many species facing extinction within decades. Tropical rainforests are losing species faster than they can be cataloged, with entire ecosystems disappearing before their biodiversity can be documented. Deforestation rates in the Amazon exceed 10,000 square kilometers per year, eliminating habitat for thousands of species. Southeast Asian rainforests face even higher deforestation rates as palm oil plantations replace primary forest. Each hectare of tropical rainforest contains 200 to 300 tree species and thousands of insect species, many found nowhere else on Earth. The rapid pace of forest conversion means that most species disappear before scientists can study their ecology, genetics, or potential medical applications. The magnitude of species loss in tropical regions approaches the levels seen during the Big Five extinction events. Tropical rainforests contain 50% of all species on Earth, but cover only 6% of land surface. Deforestation rates of 1% per year in some regions translate to extinction rates of 1,000 to 10,000 species per year in single ecosystems. The concentration of endemic species in small areas means that local habitat destruction can eliminate entire evolutionary lineages. Unlike previous extinctions that unfolded over millions of years, the current crisis compresses mass extinction into decades rather than millennia. The Big Five extinctions occurred over timescales of 100,000 to 2 million years, providing some species with opportunities to adapt or migrate. Current extinction rates operate over timescales of decades to centuries, faster than evolutionary adaptation can occur. The temporal compression means that natural selection cannot operate effectively to produce survivors. Species face environmental changes that exceed their adaptive capacity within single generations. Yet behind these staggering numbers lies an even more immediate threat that is accelerating every aspect of the extinction crisis. Climate chaos, the accelerating trigger. Rising global temperatures are pushing Earth's climate systems past critical thresholds that trigger irreversible changes. The year 2024 marked the hottest temperatures ever recorded, with global averages reaching 1.5 degrees Celsius above pre-industrial levels. Ocean temperatures broke records in every major basin, with surface waters reaching levels that stress marine ecosystems beyond their survival limits. Arctic regions experience temperature anomalies of 4 to 6 degrees Celsius above normal, accelerating ice loss at unprecedented rates. Climate tipping points are cascading into runaway effects that amplify warming beyond human control. The West Antarctic ice sheet has reached irreversible collapse, where continued melting occurs regardless of future emission reductions. Permafrost across the Arctic melts faster than projected, releasing methane and carbon dioxide that accelerate warming further. The Amazon rainforest has shifted from carbon sink to carbon source in many regions, releasing stored carbon instead of absorbing it. These feedback loops create self-reinforcing cycles where initial warming triggers additional warming through natural processes. Arctic ice loss accelerates sea level rise beyond scientific projections through mechanisms that models failed to predict. The Greenland ice sheet loses 280 billion tons of ice annually, double the rate measured in the 1990s. Antarctic ice loss has tripled since 2012, with major glaciers showing signs of unstoppable retreat. Thermal expansion of seawater adds additional volume as ocean temperatures rise. Ice sheet dynamics operate through processes that create nonlinear responses to warming. Meltwater lubricates glacier bases, causing them to slide faster toward the ocean. Warm water infiltrates beneath ice shelves, melting them from below and destabilizing the glaciers they support. Species are being forced to migrate faster than they can adapt as climate zones shift toward the poles at rates of 5 to 10 kilometers per decade. Mountain species face upward migration as temperatures rise, but many reach elevation limits where no suitable habitat exists. Arctic species lose sea ice habitat that cannot be replaced by terrestrial alternatives. Tropical species encounter temperature thresholds that exceed their physiological tolerance limits. The speed of climate change outpaces the ability of most species to migrate or adapt through genetic changes. Plant communities face particular challenges as climate zones shift faster than seed dispersal and establishment can occur. Tree species migrate at rates of 100 to 1,000 meters per year through natural seed dispersal, but climate zones shift 10 times faster. Forest composition changes as heat-tolerant species colonize areas where cold-adapted species can no longer survive. Agricultural regions lose reliability as temperature and precipitation patterns shift beyond crop tolerance ranges. Phenological mismatches occur when flowering, fruiting, and other biological events fall out of sync with seasonal cycles that pollinators depend on. Extreme weather events fragment habitats and destroy breeding grounds through increased frequency and intensity of storms, droughts, and floods. Hurricane intensity has increased as warmer ocean temperatures provide more energy for storm development. Drought frequency has doubled in many regions, creating stress that weakens ecosystems and increases wildfire risk. Flooding events eliminate nesting sites and disrupt reproduction cycles for many species. Heat waves create thermal stress that exceeds tolerance limits of many organisms, causing direct mortality and reproductive failure. Coral reefs are collapsing as ocean temperatures exceed survival thresholds that evolved over millions of years. The Great Barrier Reef has experienced multiple bleaching events since 2016, with some areas showing 95% coral mortality. Caribbean reefs have lost 80% of their coral cover since the 1980s due to warming waters and disease outbreaks. Coral bleaching occurs when temperatures exceed normal ranges by just 1 to 2 degrees Celsius, causing corals to expel their symbiotic algae and lose their primary food source. Recovery requires years of stable conditions that rarely occur as ocean temperatures continue rising. Ocean acidification compounds thermal stress on coral reefs by making it harder for corals to build their calcium carbonate skeletons. The combination of warming and acidification creates conditions that many coral species cannot survive. Coral reproduction fails when temperatures exceed critical thresholds during spawning seasons. Juvenile corals cannot establish successfully in increasingly hostile ocean conditions. The loss of coral reefs eliminates habitat for 25% of all marine species, creating cascading effects throughout ocean ecosystems. Permafrost melting releases stored carbon in feedback loops that accelerate warming beyond human emission rates. Arctic permafrost contains twice as much carbon as exists in the entire atmosphere, locked in frozen soils that accumulated organic matter for thousands of years. Rising temperatures thaw this permafrost, allowing bacterial decomposition that releases CO2 and methane into the atmosphere. Methane has 25 times more warming potential than CO2, making permafrost emissions particularly dangerous for climate stability. The feedback creates a situation where warming causes more warming through natural processes that humans cannot control. Changing precipitation patterns turn forests into deserts as rainfall decreases and evaporation increases in many regions. The Mediterranean basin experiences desertification as annual rainfall decreases and temperatures rise. Southwestern United States faces megadrought conditions that stress forest ecosystems beyond their survival limits. Amazon rainforest regions shift from wet to dry seasons that last longer and become more intense. These changes eliminate forests that took centuries to develop, replacing them with grasslands or bare soil that cannot support the same biodiversity. Current warming rates exceed even the most catastrophic ancient climate shifts in both speed and magnitude. The Paleocene thermal maximum warmed the planet by 5 to 8 degrees Celsius over 20,000 years, while current warming approaches similar magnitudes over centuries. The Great Dying involved warming of 10 degrees Celsius over 60,000 years, but current emission rates could produce comparable warming in just a few centuries. The compression of climate change into human timescales creates conditions that have never existed in Earth's history, pushing both individual species and entire ecosystems beyond their evolutionary limits. This acceleration of environmental change represents just one component of a larger crisis that scientists now recognize has already begun. The Sixth Extinction, already here. Scientific consensus confirms that the sixth mass extinction is not approaching, but already underway. Leading extinction researchers from universities worldwide agree that Earth entered a new mass extinction event decades ago. The evidence appears in population surveys, species monitoring data, and extinction rate calculations that exceed the thresholds used to define previous mass extinctions. Unlike the Big Five events that took millions of years to unfold, this extinction crisis has compressed into centuries. The International Union for Conservation of Nature reports that 28% of assessed species face extinction risk, with rates accelerating across all major taxonomic groups. We are living through an extinction event comparable to the Big Five mass extinctions that shaped Earth's history. Current species loss rates match or exceed those calculated for the Great Dying, the Asteroid Impact that killed dinosaurs and other ancient catastrophes. The magnitude becomes clear when examining vertebrate populations, which have declined by 69% since 1970 according to the Living Planet Index. Invertebrate populations show even steeper declines, with insect biomass dropping by 75% in some regions over just 27 years. These population crashes mirror the fossil evidence from previous mass extinctions, where abundant species disappeared rapidly from the geological record. Megafauna extinctions over the past 50,000 years mark the beginning of this crisis, coinciding with human expansion across continents. Australia lost 85% of its large animal species within 10,000 years of human arrival 50,000 years ago. North America lost 70% of its megafauna, including mammoths, giant ground sloths, and saber-toothed cats around 13,000 years ago. Madagascar lost 17 species of giant lemurs, elephant birds, and other large animals within 2,000 years of human colonization. These extinction waves followed human migration patterns with remarkable consistency, suggesting that human hunting and habitat modification drove most large animal extinctions. The Quaternary extinction event that eliminated megafauna represents the opening phase of the sixth mass extinction. Large mammals faced particular vulnerability because of their slow reproduction rates and high energy requirements. Human hunting pressure, combined with climate change at the end of the last ice age, created conditions that large species could not survive. The disappearance of megafauna altered entire ecosystems by removing seed dispersers, grazers, and predators that maintained ecological balance. Human expansion has eliminated species faster than any asteroid impact through systematic habitat destruction and resource exploitation. The asteroid that killed dinosaurs caused global devastation within months, but human activities have maintained extinction pressure for millennia. Agricultural expansion eliminates natural habitat at rates of 10 million hectares annually. Urban development fragments remaining ecosystems into isolated patches too small to support viable populations. Industrial activities pollute air, water, and soil with toxic compounds that accumulate in food webs and cause reproductive failure in wildlife. The combination of climate change, habitat loss, and pollution creates a perfect storm that overwhelms species' adaptive capacity. Each threat alone would challenge wildlife populations, but their interaction creates synergistic effects that multiply the damage. Climate change forces species to migrate toward cooler regions, but habitat fragmentation blocks migration routes. Pollution weakens immune systems and reduces reproductive success, just as species need maximum fitness to survive environmental changes. Island ecosystems are collapsing as invasive species overwhelm native life, that evolved without defenses against foreign competitors. Oceanic islands contain 15% of all species despite covering less than 5% of Earth's land surface. These isolated ecosystems developed unique species over millions of years of separation from mainland communities. Human transportation has broken down these barriers by introducing continental species that outcompete native island life. Hawaii has lost 71% of its native bird species to invasive predators, diseases, and habitat conversion. New Zealand has lost 44% of its native bird species since human arrival. Even common species are now experiencing rapid population declines that signal widespread ecosystem degradation. Monarch butterfly populations have declined by 85% since 1996 despite their former abundance across North America. Grassland birds have lost 53% of their populations since 1970, with species like meadowlarks and bobolinks becoming rare in areas where they were once numerous. Common farmland species in Europe have declined by 57% since 1980 as agricultural intensification eliminates habitat diversity. These declines in previously abundant species indicate that ecosystem degradation has reached critical levels. The extinction debt means many species are already doomed, even if we act now to reduce threats. Habitat fragmentation has isolated populations below minimum viable sizes, guaranteeing their eventual extinction through genetic problems and demographic fluctuations. Climate change has already committed many species to extinction by altering their habitat beyond recovery timescales. Pollution has accumulated in ecosystems at levels that will continue causing mortality for decades, even if emissions cease immediately. The time lag between cause and effect means that current conservation efforts cannot save species already caught in extinction vortexes. Ecosystem collapse threatens our own species through the breakdown of natural services that support human civilization. Pollinator decline threatens food security as crop yields decrease without adequate pollination. Soil degradation reduces agricultural productivity while increasing erosion and flooding. Water cycle disruption affects freshwater availability as forests and wetlands disappear. Ocean acidification threatens marine food webs that provide protein for billions of people. Climate regulation fails as carbon-storing ecosystems are destroyed, accelerating global warming. This extinction event is unique because it's driven by a single species that has the power to change course. Previous mass extinctions resulted from volcanic eruptions, asteroid impacts, or other natural disasters beyond biological control. The current crisis stems from human activities that could be modified through conscious choice and technological innovation. We possess the knowledge to identify threatened species, understand extinction processes, and implement conservation strategies. The question is whether human societies will act quickly enough to prevent this extinction event from matching the severity of the big five catastrophes that reshaped life on Earth. Yet, even as species disappear at unprecedented rates, some remarkable recovery stories demonstrate that extinction is not always inevitable when humans choose to intervene. Hope in the darkness, what we can still save. The California condor soared on the edge of extinction in 1987 when only 27 birds remained alive. Captive breeding programs rescued the species from total annihilation through intensive management and careful genetic planning. Biologists captured every remaining condor and began breeding them in specialized facilities designed to maximize reproductive success. The program required decades of patience as condors reproduce slowly, taking 6 years to reach sexual maturity and laying only one egg every 2 years. Today, over 500 condors exist, with more than 300 flying free across California, Arizona, and Utah. The recovery demonstrates that even species reduced to tiny populations can be saved through dedicated conservation effort. Gray wolves returned to Yellowstone National Park in 1995 after 70 years of absence, triggering ecosystem recovery that exceeded all scientific predictions. The reintroduction began with 31 wolves captured in Canada and released into the park ecosystem. Wolf predation controlled elk populations that had overgrazed vegetation along rivers and streams. Reduced browsing pressure allowed willows and aspens to regenerate, stabilizing stream banks and creating habitat for beavers. Beaver dams restored wetland ecosystems that supported diverse bird and amphibian communities. The cascade of ecological changes spread throughout the park as natural predator-prey relationships resumed their historical function. Protected areas and wildlife corridors can halt biodiversity loss by providing safe habitat and connecting fragmented populations. The Yellowstone to Yukon Conservation Initiative links protected areas across 1.2 million square kilometers, creating migration routes for grizzly bears, wolves, and other wide-ranging species. Corridor design considers the movement patterns of target species, ensuring that connections provide suitable habitat rather than just physical pathways. Bridge overpasses and tunnel underpasses allow wildlife to cross highways safely, reducing vehicle mortality and maintaining genetic flow between populations. Marine protected areas create refuge zones where fish populations can recover and spill over into adjacent fishing grounds. Genetic rescue programs are saving critically endangered species through advanced reproductive technologies and careful population management. The black-footed ferret recovery program uses artificial insemination and cryopreserved sperm to maintain genetic diversity in captive populations. Genetic analysis identifies the most genetically valuable individuals for breeding, preventing inbreeding while preserving rare alleles. Cross-fostering programs place endangered species eggs or young with closely related surrogate parents, increasing reproductive success rates for species with poor parental care. Ecosystem restoration can bring back entire food webs by re-establishing foundation species and natural processes. Coral reef restoration projects grow coral fragments in nurseries before transplanting them to degraded reef areas. The transplanted corals recruit fish and other marine life, rebuilding complex reef ecosystems within decades. Wetland restoration removes drainage tiles and restores natural hydrology to former agricultural land. Native plant communities establish quickly once water levels stabilize, providing habitat for waterfowl, amphibians, and invertebrates. Prairie restoration uses prescribed fire and native seed mixes to recreate grassland ecosystems that support diverse plant and animal communities. Citizen science and technology are accelerating conservation efforts by engaging millions of volunteers in data collection and monitoring. The eBird project collects over 100 million bird observations annually from citizen scientists worldwide, creating massive databases that track population trends and migration patterns. Camera traps operated by volunteers monitor wildlife populations in remote areas where professional biologists cannot maintain regular presence. Smartphone apps allow citizens to identify species and report sightings, contributing to biodiversity surveys and conservation planning. Rewilding projects are restoring natural processes to degraded landscapes by reintroducing native species and removing human interventions. The Pleistocene Park project in Siberia reintroduces large herbivores like bison and horses to restore grassland ecosystems that existed before human hunting eliminated megafauna. Grazing by large animals maintains grasslands that store more carbon than forests in permafrost regions. Beaver reintroduction projects restore wetland ecosystems by allowing beavers to build dams and create habitat complexity. Predator reintroduction programs restore natural selection pressure that maintains healthy prey populations and reduces overgrazing. Some ecosystems can recover faster than expected when threats are removed and restoration efforts provide initial support. Abandoned agricultural land can develop into forest within 50 years if seed sources remain available and soils retain adequate fertility. Urban brownfields can be transformed into productive wildlife habitat through soil remediation and native plant establishment. Coastal marsh restoration can rebuild productive estuarine ecosystems within decades using sediment deposition and native plant propagation. Marine ecosystems show rapid recovery when fishing pressure is reduced and habitat destruction ceases, with fish populations rebounding within years of protection. International cooperation has successfully protected migratory species through coordinated management across political boundaries. The Convention on Migratory Species coordinates protection efforts for animals that cross international borders during migration. Waterfowl hunting regulations are synchronized across North America to ensure sustainable harvest levels throughout migration routes. Sea turtle protection programs coordinate nesting beach protection with fishing regulations to reduce mortality throughout turtle life cycles. Individual actions can contribute to species recovery through habitat creation, responsible consumption, and support for conservation organizations. Backyard habitat creation provides stepping stones for wildlife movement between larger protected areas. Native plant gardens support pollinators and provide food for birds and other wildlife. Reducing pesticide use protects beneficial insects and prevents toxic accumulation in food webs. Consumer choices that support sustainable agriculture and forestry practices reduce pressure on natural ecosystems. Conservation success stories provide models for protecting other threatened species and ecosystems. The recovery of humpback whales from near extinction to stable populations demonstrates that marine mammal conservation can succeed when hunting pressure is reduced. Peregrine falcon recovery through DDT bans and captive breeding shows that pollution control can restore bird populations. Bald eagle populations have recovered from 417 pairs in 1963 to over 70,000 pairs today through habitat protection and chemical restrictions. These examples prove that conservation efforts can reverse population declines and restore ecological function. While the sixth extinction is underway, its ultimate severity depends on actions we take now. The difference between a moderate extinction event and a catastrophic one depends on how quickly we implement conservation measures and reduce threats to biodiversity. Every species saved today contributes to ecosystem stability and resilience. Every habitat protected provides refuge for species to survive current threats and recover when conditions improve. The choices we make in the next few decades will determine whether this extinction event matches the severity of the Big Five or becomes a manageable crisis that preserves most of Earth's biodiversity for future generations. Human actions have created the first extinction crisis that intelligence can potentially control. We are living through Earth's sixth mass extinction, a biological catastrophe comparable to the asteroid that killed the dinosaurs or the Great Dying that eliminated 96% of marine life. Unlike previous extinctions driven by volcanic eruptions or cosmic impacts, this crisis stems from human activities that we can still modify. The fossil record teaches us that mass extinctions reshape life on Earth permanently, but it also reveals that some species always survive to rebuild ecosystems. Understanding extinction history gives us the knowledge to prevent the worst outcomes through conservation action and environmental protection. Future generations will judge whether humans caused the sixth extinction or prevented it from matching the severity of the Big Five.